How else does Windows protect its users? The first mechanism is ASLR. The ASLR mechanism is designed to prevent buffer overflow attacks, in particular, automated buffer overflow attacks. In the future, we will speak in more detail about these attacks. For now, let's remember that in order to carry out an attack of this type, the specified library need be found in the memory. We need to know at which address in the operating memory a certain library is allocated. We need to know how it works and how it's built. To hinder such automation, newer Windows systems, every time they're launched, load the system libraries in a different area of the memory. Cells with addresses from 1 to 255 are chosen at random. Exploits have a 1 in 255 chance that this will work. We can trace such an operation in Process Explorer. In a moment, we will have the opportunity to see it. Unfortunately, the ASLR mechanism is not mandatory. System libraries are covered, but programs are not covered. The protection of programs in this way is the decision of the user. In the past, in order for programs to be protected by ASLR and other mechanisms such as DEP, which we'll talk about in a moment, it was necessary to set the corresponding bit in the header of a given program. It was necessary to have access to the source code or open the file in a hex editor and manually edit the appropriate bits. Not many users or administrators wanted to do this. The solution came again from Microsoft. We have a tool that allows enabling this protection also for programs that do not require it, without any interference in their privileges. In a moment, we'll see this. This tool is called the Enhanced Mitigation Experience Toolkit, or EMET. Let's talk for a moment longer about the DEP mechanism. This is another way to defend against the same threat. DEP is available on 32-bit platforms as long as the hardware supports the mechanism. That is, if the processor is compatible with the solution. In the case of companies AMD and Intel, these solutions are called differently, but their task is the same. The point is that in contemporary PC architecture, there is no dedicated storage area for data or a memory area for code. There is one RAM, virtual address space memory. What's in it depends on the program which allocated it. It could be such that when overriding a return code from a function call, again we're dealing with buffer overflow attacks, the attacker tries to execute code that's placed in a data area. For example, by passing it as a parameter invoking some program function. The point is that somehow from the outside, the manner in which the program runs can be changed, without changing its code. The DEP function means some areas of memory are data only. The attempt to execute code contained in such a designated memory area results in an error. The program is automatically stopped by Windows, at least in theory, because lately there's been increasing talk that in the case of Intel processors, the low level of security was overcome and programs are forced to execute code labeled as data only. Let's see then how ASLR and DEP work and how they protect third-party software using the EMET program. We'll take a look at only part of the first. Run Process Explorer as a privileged process. Then select the Explorer process and in the bottom window display the library. This way we'll see what libraries are used by the Explorer exe process. These are shared libraries or shared data areas. We can see, among other things, at which address each library is loaded. We're particularly interested in the NTDLL library. This is a kernel system loader. The library will begin the boot process. When we switch to graphics mode, it means that NTDLL just launched. If we have the ASLR mechanism enabled, then after restarting the library, the address must be different, with a chance of 1 to 255. Now let's look at the DEP protection. Displaying the computer's advanced properties, we can accidentally click on the Settings button in the Performance section. In fact, DEP has nothing to do with performance. It may only sometimes slow the computer. Going to these settings, it appears that data execution prevention is turned on, but only for the operating system. The programs are not protected by DEP. We protect this code fragment, which is anyways most likely resistant to attack, because it is thoroughly checked in the Microsoft Corporation's Trustworthy Computing Group, the initiative that we mentioned earlier. In order to change this, we need to select a second option. From now, all programs are protected by DEP. If a program does not work, because it happens to invoke a code fragment, such as ISAPI libraries, which are located in the area of memory that cannot be invoked, we should configure the settings as seen above. This is the default configuration of the server system. There is no reason not to change it for the client systems as well. But what do we do if we've inherited a program which has been operating in our company for 10 or 15 years, its author is completely unknown, the code was lost long ago with its creator, and for some reason we still need to use it? The best thing we can do is use the Enhanced Mitigation and Experience Toolkit in order to give the program some additional security. Now we'll see how easy it is to use the EMET tool. It allows us to configure the system, such as change the DEP option, which we saw earlier in the system properties. These are global options. We already talked about DEP. We also talked about ASLR. But in the EMET program, there's one more option, which is called CHOP. Here it deals with a type of buffer overflow attack that uses structured exception handling. If a function reports an error, the code handling this exception is in a different area of the memory. Another possibility is that it reports an exception caught by another code fragment. We're dealing with a hierarchy of a structured exception handler. The attacker attempts to take advantage of this mechanism in such a way that the function that handles the error at the end of the action does not return control to the function that caused the error, but another memory address is indicated. This will be a memory address where the attacker probably already managed to place his own code. We can use the CHOP mechanism to protect us from such attacks. This mechanism works quite simply. It saves the last address on a list of an exception handling function. Now, when an error handling finishes and the program execution control returns to the main program, CHOP checks to see if it went outside the stored address. If so, it immediately stops the program. In the EMET program, we see a list of certain processes and whether or not they're protected by DEP. What can we do to protect an additional program? We click the Configure Apps button and we indicate a program that we'd like to protect. Suppose that we'd like to protect a program from the sysinternal suit series. Let's select here the ProCXP program. For ProCXP, we can enforce DEP protection or CHOP protection. We can also enable ASLR and additionally protect the program from the type of attack characteristic for Internet Explorer, called heap spray. In a heap spray attack, the attacker tries to multiply its code fragment which is injected, for example, as a parameter invoking a function. The more copies of the attacker's mini program that are placed on the heap, the greater the chance that when it later overwrites the return address, it will indicate its own code to execute. Heap spray allocates memory on the heap for the program in advance and makes sure that jumps in specific addresses are controlled. Therefore, the question is raised: how can ASLR be forced for a program that it does not support? The program always wants to load at the same address. The EMET program allocates memory for a program that we indicate, then it makes it available. Of course, EMET supports ASLR, so each time a given application starts, in our case ProCXP, it will load it under a different operating memory address. This actually ends our protection. After running Process Explorer, we see it in the EMET program. DEP protection is enabled for our process, and it is virtualized and protected by EMET according to the options we previously set. The same application that was previously susceptible to buffer overflow attacks is now resistant to these attacks, without changing even a single line of code.